Hello, everyone, and welcome for another edition of our NACE Calgary webinar program. I'm your host, Brett Johnson. So today I have the pleasure of welcoming Dr. Frank Cheng back to our webinar platform. Frank is a professor at the University of Calgary and the Canadian Research Chair in Pipeline Engineering. Frank has authored 4 books and over 260 journal articles in the world of pipeline corrosion, stress corrosion cracking, and integrity management. He was elected a Fellow of NACE International, of the UK Institute of Corrosion, and of the UK Institute of Materials, Minerals, and Mining. He has achieved an abundance of distinguished awards, including the 2014 Welding Award, the 2021 Technical Achievement Award of NACE, the 2017 Metal Chemistry Award, and the 2019 Distinguished Materials Scientist Award from the Canadian Metallurgy and Materials Society, the 2021 International Association of Advanced Metals or Material Metals, and most recently, the 2022 International Brian Ives Lectureship Award. Frank is also serving as the editor-in-chief for the journal Pipeline Science and Engineering. Frank, your achievements have grown significantly since the last time we hosted you, and I'm really excited you were able to join us again back on our platform.
Oh, hi, everyone. Thank you, Brett, and also thank you, NACE Calgary, to invite me back to the webinar activity. So everybody knows hydrogen is a hot keyword and is attracted to the research and the industry from the whole world. My research activity on hydrogen is can be back about 20 years ago when I researched the hydrogen-steel interaction, particularly hydrogen embrittlement, hydrogen-induced cracking. And today in my talk, I will introduce the material safety perspective when we repurpose the existing pipeline for hydrogen transport. And I will particularly detail under the technical challenge and to how it's related to use the existing aged pipeline and in hydrogen environment. And I will also detail the essential difference between the hydrogen embrittlement environment problem happening in the gas environment compared with the liquid solution phase environment. Anyhow, so I hope you enjoyed today's talk. I will do my best and to cover the interested topics and as more as possible. Bert, back to you.
Awesome. Well, I'm looking forward to it. But before we jump into that, it's important to note that none of what we'd be able to do would be possible without our annual sponsors. Their contributions allow us to be able to provide this webinar series to our membership at no charge. So today I'd like to highlight one of our gold sponsors, ChampionX. So ChampionX is proud to be a gold level sponsor of NACE and an active contributor of global and local NACE seminars, technical groups, and events. They're a global leader in chemistry programs and services, drilling technology, artificial lift solutions, and automation technologies for the upstream and midstream oil and gas industry, and are committed to safely and sustainably unlocking energy. ChampionX continuously strives to help their customers meet their goals of enhancing operational efficiencies and minimizing environmental impact by reducing their carbon footprint, overall waste production, and greenhouse gas emissions. And of course, all of our other annual sponsors are a huge reason why we can do what we do. Our sponsors help fund several initiatives that NACE Calgary takes on to promote the knowledge of corrosion, sustainability, and asset integrity to our industry and the next generation of engineers. To each one of our sponsors, we sincerely thank you for continued support. So if you haven't had the chance yet to check out our YouTube channel, please go to our website at nacecalgary.ca. And from there, you can find the direct link to the channel and a list of all of our past presentations to view up on. So also, if you enjoyed presentations like this one and are looking for an opportunity to see more like it and network again with our community up in Edmonton, be sure to check out the NACE Northern Area Western Conference, scheduled to be run from April 11th to the 14th at the Edmonton Convention Center. So registration is now live at nawc2022.com. So Frank is going to be giving his presentation live. Be sure to stick around after the presentation, as we'll then move into a live Q&A session. Please submit your questions in your Zoom client by clicking the Q&A button on the screen. If you're joining us from YouTube Live, please enter your questions into the comments there and I'll be sure to ask them. So without further ado, Frank, go ahead and share your screen and take it away.
All right, thank you, Brad. Hello again. Thanks, NACE Calgary and just have an opportunity to talk about using the existing pipeline for hydrogen transport. I will discuss the safety and integrity issues from the materials perspective. So as I mentioned a moment ago in today's talk, I will very quickly review why pipelines for hydrogen transport. And then I will talk about the fundamentals about the hydrogen embrittlement as a threat to integrity of pipelines. So this part is serving as education purpose. And next, I will use much more time to talk about the hydrogen embrittlement program and happening in the gaseous environment, and especially for high pressure hydrogen gas. So next, and the technical challenge related to use the existing aged natural gas pipeline for hydrogen transport. And finally, I will give the conclusive remarks, and particularly I will give 2 lists and to identify the gaps to be filled if we want to repurpose the natural gas pipeline for hydrogen purpose. Okay, so I don't want to use lots of time because you can find from internet lots of different resources, and the world is hiding for hydrogen. And you can see lots of data in Canada, in US, other countries, the hydrogen production and the hydrogen demand are increasing. At the same time, you can also find the literature related to the governmental hydrogen strategy and the hydrogen roadmap, particularly our province, Alberta, also published a hydrogen roadmap. In terms of the hydrogen economy, it included 3 interrelated sections: hydrogen production, hydrogen delivery, and hydrogen use. And from this entire value chain, and you can see efficient, economic, and safe hydrogen transport is pretty critical to realize the full-scale hydrogen economy. Of course, as a pipeline researcher, we focus on the second stage, hydrogen delivery. Before we talk about the hydrogen transport, and let's look at the phase diagram. This is very fundamental, but it's very critical, and it will influence lots of things related to the hydrogen. Okay, anyhow, so to be briefly, you can see the critical point from the phase diagram for hydrogen is listed, the information is listed here. I don't repeat the number. And the normal temperature and pressure, and hydrogen will exist as a gas. So if you want to liquefy the hydrogen, you can see from the diagram, there is only a very small range. Hydrogen can become liquid in terms of the pressure and the temperature. At the same time, hydrogen is very light. The density is given here. So that's why hydrogen has a high energy content per unit of weight, but a very low hydrogen content per volume. So this property is important in terms of the economic, safety, and efficiency consideration when we transport hydrogen. Okay, so right now hydrogen can be transported by truck tanks and tube trainers. Of course, it can also transported by pipelines. And when I give this table to list some of the basic information in terms of the cost, capacity, and the efficiency. So you can see directly, pipelines is offer lots of advantage. And the US DOE just issued a document and stated clearly, transporting hydrogen through the existing pipelines is a low-cost option for delivering large volume of hydrogen. Okay, so currently there is a very limited mileage of pipelines used for hydrogen service, and mostly are located in US and Europe. So in the United States, the hydrogen pipelines mainly located in the Gulf area. So that's normal because the oil production and the refinery located there. And in China, there is also a very limited and distance of pipelines for hydrogen service. But I want to mention the European initiative. It's called the European Hydrogen Backbone. and it's developed in 2020. So it's issued develop the plan and in the next 20 years. So you can see in European countries, the new pipeline and the existing pipeline will be used together and to target the, the well-developed connection in the European countries for hydrogen transport. Okay, with the increased hydrogen demand, we will expect the hydrogen pipelines will progressively installed. And which type of hydrogen pipeline do we have? Basically, we can build the new pipeline and for dedicated hydrogen transport. And in general, the pure hydrogen mostly used in transport and power sectors. From the graph on the right side of the slide, you can see power generation by hydrogen. Actually, by 2050, this is forecast into the 2050. Power generation by hydrogen, not a big percentage. For the transport purpose, hydrogen is mainly used for the highway duty bit sectors, transportation sectors. So this is the first type, is the dedicated hydrogen transport pipelines. Of course, we can also blend the hydrogen with the methane. We call the transported through the existing gas pipelines. So the blended form of hydrogen mostly used in manufacturing and building sectors. You can also see from the graph on the right side, and the building heating and the cooking, and roughly by 2050, 20%. But mostly the hydrogen transported by this form is used in industry. Okay, because when we build, if we want to build a new pipeline for dedicated transport of hydrogen, and the super high initial capital cost is a major barrier. So that's why, and the industry and the government tend to go to use the existing natural gas pipeline to transport the hydrogen, and through the blending of hydrogen with the natural gas. So if we realize this strategy and the plan, and I summarize the 4 areas of technical challenges we have to overcome or we have to address. First one is the type of materials. So if the material is safe enough and to transport the hydrogen and the natural gas blending, or what's the optimum operation conditions. Second one related to the blending operation and some of the tools, inspection tools, leak detection, something like that. Number 3, integrity. Inline inspection tools can be used in hydrogen pipelines without influence the operation. Finally, is the safety for users. So on today's talk, I will focus on the first one as the pipe materials comparability with the hydrogen transport. Okay, when we read the literature and the different report, and when the steel used in the hydrogen environment, and I believe everybody in the meeting room and realize our problem, hydrogen embrittlement. So what is hydrogen embrittlement? So this is a general term referring the degradation of metals because of the hydrogen metal interaction. So firstly, I want to give our first highlight in today's talk. Hydrogen embrittlement, the hydrogen means what? That means the hydrogen atom, H, okay? So hydrogen usually can exist in 3 physical forms. Hydrogen atom H, hydrogen molecule H2, and the hydrogen ions H+. So hydrogen embrittlement means H, hydrogen atom. So that's the first thing. Okay, after hydrogen embrittlement happens, usually it can show the multiple modes of the metal degradation. So hydrogen can cause the cracking. We call it HIC. So you can see the bottom picture on the left side, and the sharp crack developed through the metal and can fill the structure. Hydrogen-induced cracking usually happen on high-strength steels. The second mode is a hydrogen ballisting. Hydrogen and hydrogen combine together to form the hydrogen bubble, hydrogen gas, to increase the local pressure to cause the ballisting and of the steel. So usually happen on low-strength steels. Third one is very common, and you can see from stress strain curve on the bottom, the right side, and it can cause the loose in ductility and the elongation. Okay, highlight 2 in today's talk. In some literature and report, and a term we call the hydrogen attack or hydrogen corrosion, and also included in the degradation of the metals. But I will emphasize hydrogen attack or hydrogen corrosion does not apply for pipelines, because this phenomenon only happen for the temperature more than 250 degrees. So we don't worry if we use a pipeline to carry hydrogen. This problem will not happen. Okay, hydrogen-induced cracking is the most dangerous mode of hydrogen embrittlement for engineering structure. So the cracks can form internally and from the metal surface, depends where the hydrogen located, and to reach the cracking condition. At the same time, depends on the environment. H2S is available. All the crack hydrogen is introduced by over cathodic protection, and we can also see the different features of the cracks related in terms of orientation of the stress or different phenomenon of the crack and the growth. And you can see lots of different terms describe the hydrogen-induced cracking. But the common thing is the crack is caused by hydrogen, of course, combined with other conditions I will talk about later. All right, when we talk about the hydrogen-induced cracking of the metals, such as the pipeline steel, and please don't forget, the pipeline is welded infrastructure. So the hydrogen-induced cracking as a welding area is particularly important. So there are 3 reasons. First one, pipeline welding area has a unique methodological microstructure. So you can see from the metallographic picture on the right side, and the base steel, the heat affected zone HAZ, and the welded metal, they have the different microstructure. And particularly in the middle one, HAZ, there in addition to F is a ferrite, B is a bainite, and it also have C is a samtite. So this one is a hard and brittle phase, can make the hydrogen-induced cracking more sensitive. At the same time, the welding area also has the local high stress concentration. So we just use a model to simulate. At the HAZ, you can see the stress has a peak in this area that's associated with the stress concentration. Number 3, in the welding area, depends on the different conditions, there is always a hydrogen accumulation. So you can also see from this figure, we found the hydrogen concentration has a peak as the HAZ and interface between HAZ and the welded metal. So, and let's come to the highlight 3. When hydrogen-induced cracking happens, it depends on 3 conditions. Number 1, steel metallurgy. Number 2, local stress. Number 3, hydrogen concentration. So the welding area has a unique feature in the 3 conditions. All right, so how a hydrogen-induced cracking or hydrogen embrittlement happens on pipeline steel? So usually have 6 steps. And the first one, I just mentioned in the beginning of my talk, hydrogen embrittlement means the hydrogen atom induced embrittlement. So that's why first step, how hydrogen atoms are generated from the environment condition. So that's the first step. After hydrogen atom produced, and it will touch on the steel surface. So that's a second step, adsorption, ADS. Okay, ADS hydrogen will go inside the steel, become absorption, ABS hydrogen. So that's number 3. When hydrogen goes into the metal or steel, and it's tended to diffuse in the crystal lattice of the steel, that's a diffusion, number 4. And all the steels usually have a typical methodological features and mechanical defects. So hydrogen can become trapped. So that number 3 step, number 5 step is hydrogen trapping. So when the stress hydrogen and the metal structure meet the condition, finally it can cause a cracking. So you only have 6 steps and work to cause a cracking of the steel because of hydrogen. So when we talk about, because today's topic focus on hydrogen pipelines, so that's why we need to include the influence of the gas environment. So the first 3 steps, hydrogen generation, hydrogen adsorption, and hydrogen absorption. These 3 steps depends on environment. So that means a gas environment and the solution environment will influence the first step. Consequently, the overall hydrogen embrittlement will be totally different. And if we target the gas phase hydrogen and the solution phase hydrogen. So that's why I summarize the highlight 4. When we talk about the hydrogen embrittlement problem, and we do realize the hydrogen atom generation, adsorption, and absorption process will depend on environment. Okay, so there are 6 steps for the hydrogen embrittlement to happen. So let's firstly look at the steps that are identical in both environment. And that's the last 3 steps. And it's not dependent on the environment. So we discuss the last 3 steps first. That's a hydrogen diffusion, hydrogen trapping, and hydrogen-induced cracking. Okay, so I do not want to talk too much about the fundamentals of the steel metallurgy and crystalline structure. So we just realized after hydrogen atom goes into steel, become hydrogen ABS. So it's tended to located in the tetrahydrosides because everybody knows. So the steel is mainly combines with the Fe atoms. So Fe atoms and put together to form the space between them. So this space is typically we call is a void. And the hydrogen ABS will locate it in the tetrahydrosides and surrounded by 4 iron atoms, not 8, and based on the different energy level. So we have the detailed calculation of the energy, but I do not talk too much about the calculation. Okay, so after hydrogen ABS located in TS site, and this just means certain steel and the certain stress condition have a tolerance to the hydrogen can be trapped. So that means not a certain amount of hydrogen can cause cracking. So given steel and the certain stress condition, you do not expect a cracking problem if hydrogen goes into the metal because there is a tolerance of the steel to the hydrogen atoms. Okay, if the hydrogen atom is uniformly distributed in the steel at the TS sites, so that's good because what? A uniform distribution can make the local concentration below a tolerance hydrogen concentration level. So if this happens, we do not worry hydrogen embrittlement problem. So that's why if you can uniformly make the hydrogen atoms distributed in the steel, so that's a favored condition. Okay, at the same time, if the hydrogen is trapped or located at the 1 TS site, it can also diffuse, go to another TS site. So the diffusion between TS and another TS actually do not need a significant driving force because the hydrogen atom has a small size, and from the 1 TS go to another TS, usually only cause a little bit lattice distortion. So that's why the energy barrier is not significant. So hydrogen atom trapped at the TS site can diffuse freely inside the steel. Okay, so if it's happen uniformly in the steel, we don't worry hydrogen embrittlement. Okay, unfortunately, all steels must include different types of the methodological features. So this feature can trap hydrogen, make the hydrogen locally concentrated in this area. For example, all the steels will include lots of dislocation. So this is a typical linear defect in the steel. The dislocation density can significantly go up if the steel is under stress condition. At the same time, hydrogen can also located as a green boundary or face boundary or different voids or lots of other defects. So this trapping as these defects can make what? Can make the local hydrogen concentration is much more than the uniform distribution concentration. Okay, so what's the reason hydrogen can be trapped at these methodological defects? So basically, there are two mechanisms. I just very briefly to introduce the two mechanisms. First one we call is the electrical field interaction mechanism. So hydrogen can neutralize the local electricity as these defects to make the charge become balanced. So this is a driving force. Hydrogen can become locally trapped. The second mechanism is a stress field interaction. So local stress concentration can create a little bit more space to host hydrogen. But anyhow, so this is a two basic mechanism. Hydrogen can become trapped. Depends on the trapping energy level. In the steel, there are two types of hydrogen traps. One we call it a reversible. Reversible means the hydrogen gets trapped. Is also very easy to leave these traps. So for example, dislocations or no angle green boundaries, they are reversible traps. Another one is irreversible. So that means the hydrogen bonding energy is significant. When hydrogen is trapped in this location, it's not easy for hydrogen to leave this area. So for example, the non-mechanical inclusions or high angle green boundaries. So they are irreversible, okay, irreversible. So the hydrogen traps is very important. And highlight 6 is because different types of hydrogen traps included in the steel, it can make the local hydrogen concentration is more than the threshold value, consequently to cause the cracking event. So that's why you can see from this description, if we want to study the hydrogen embrittlement or hydrogen-induced cracking, it's very critical to characterize the hydrogen traps included in the steel, because hydrogen will pretty easily concentrated in this area. Even the average hydrogen concentration is very, very small, but the local concentration probably is more than threshold value to cause a cracking event. All right, so why hydrogen reach a certain concentration can cause the cracking of the steel? Of course, if you have an interest to review the mechanism, there is so many documents. And because of the time, and I do not want to have a comprehensive review of the hydrogen-induced cracking fundamentals, but basically there are two mechanisms is widely accepted. First one, we call it the hydrogen-enhanced decohesion, HEDE. Hydrogen atom can decrease the bonding strength between iron atoms. Finally, the steel will become broken. So if the HEDE mechanism is followed, and it can cause the brittle cracking of the steel, and usually the hydrogen can make the steel harder, increase the mechanical strength. So that's the first one, very quickly. Second one, hydrogen-induced local plasticity, HELP. So this mechanism means the hydrogen atom will combine with the internal dislocation to make the dislocation mobility going up. So if this mechanism applies, the steel usually becomes soft, and you can measure a decreased yielding strength of the steel. So if the HELP applies, the cracking usually have the ductile feature. Okay, so and the two mechanisms are widely accepted and will apply to explain the HIC phenomenon. So I do not want to give too much detail about the two mechanisms. Use the graph on the right side, and actually this one is also tell us For HED, HERP applies, actually it also depends on hydrogen concentration. No hydrogen concentration usually is a HERP mechanism. You can say hydrogen can make the steel soft. But if you have too much hydrogen located in the steel, that's a HEDE mechanism, makes the steel harder, can become the brittle fracture. Okay, so I just quickly skip these slides and go to next one because I have so many slides in today's talk. Okay, so and next we go to our very important topic is hydrogen embrittlement in gaseous environment. Okay, high pressure hydrogen gas. So let's look at the 6 steps. And I just mentioned first the 3 depends on environment. So if your environment is a gas or your environment is a liquid solution, and the first 3 steps will be totally different. Okay, totally different. So before I discuss the details, highlight 7 is a hydrogen atom H, not hydrogen molecule H2, goes into steel. Please, this is very important. When we talk about the hydrogen permeation into steel, that means the H goes into the steel, not H2. Okay, not H2. Then next, and it depends on the environment, it's solution-based or gas-based. I use 2 examples to explain how different the environment will influence the hydrogen generation. So a very important source for hydrogen production in liquid phase is what? Is a corrosion, right? So during the corrosion, and hydrogen can be produced by cathodic protection. H+ combined with electron produce hydrogen. So this hydrogen have 2 possibilities. One is hydrogen atom combined together becomes the H2. So this one is a gas bubble, will attach on the steel surface, cannot go into the steel. Another possibility is hydrogen ADS will become ABS. So this is hydrogen will imbritt to the steel. In general, if hydrogen produced by solution in the solution environment, the ADS goes into ABS roughly only 10%. So that means 90% will become hydrogen bubble and attach on the steel surface. So this is a solution environment. So if for the gas phase, gas environment, the hydrogen will decompose from the H2 because we carry the hydrogen gas, H2. Decomposition of H2 and produce H, then the H will goes into the steel. So you can say the generation of hydrogen atom totally different. The second one, for the given hydrogen pipelining conditions, actually we also need to think about, in addition to the pressure and the temperature, we also need to pay attention to the composition of the gas fluid. Because especially for the hydrogen and the natural gas blended. So you can say from this graph, and the top is liquid, the bottom is gas. For hydrogen embrittlement to happen, and the source must be hydrogen gas. So if you want to evaluate hydrogen embrittlement problem will happen, firstly, you need to think pressure, temperature, and the composition to determine the hydrogen gas is available in your system. Then this is the first condition you concern the hydrogen embrittlement problem. Okay, so if your decision tell you hydrogen present in the gas phase, then I just mentioned for hydrogen goes into the steel from the gas phase, and your step must be H2 decomposed into H. So this is a very critical condition for hydrogen atom generation. Then, and the pipelining condition, this reaction will really happen. So you need to do an assessment. In general, from the gas phase H2, change into atom of the hydrogen H, there are 2 mechanisms. First one is a spontaneous dissociation. So that means H2 carried in the pipeline will, under the given condition, will automatically decompose into H. That's a spontaneous dissociation. Second one, the associative adsorption. So that means the H2 will diffuse towards the steel surface, and as a surface of the steel will decompose into H. So that's a second mechanism. So, and if you want to see hydrogen embrittlement is a problem, and you need to critically evaluate, and the two mechanisms can happen under the pipeline conditions. Okay, let's look at the spontaneous dissociation mechanism first. The same thing, I don't want to go to the too much detail. Based on the free energy change calculation, we found for the spontaneous dissociation and all the possible pipelining conditions, this mechanism will not thermodynamically possible. So that means for hydrogen gas pipelines, you don't worry, spontaneous dissociation will never happen under the pipelining conditions. The second mechanism is a dissociative adsorption, but this one you can see from the free energy change. Under the pipeline operation condition, this delta G is a free energy change is lactive. So that means a lactive free energy change for this mechanism means this one really possible thermodynamically to generate a hydrogen atom, but you need to include the influence of the temperature, pressure, and the composition, particularly the methane percentage. Then you calculate the free energy change. Then you determine is it thermodynamically possible or not possible. But our calculation prove this mechanism, yes, can make the hydrogen atom generation and happens, and a hydrogen atom goes into steel. Okay, after hydrogen is generated by the second mechanism, next one is will go into the steel from outside surface, go into the inside surface. Then this process I just mentioned also depends on environment. Okay, so if the hydrogen is, we call it the cathodic hydrogen, that means the hydrogen produced from the solution phase. So this kind of the hydrogen usually has a high driving force because the cathodic hydrogen is produced by cathodic reaction. The concentration of hydrogen usually is much more than the gas phase hydrogen. The driving force is much significant, can make the hydrogen quickly go into the steel and take all the potential site for hydrogen accumulation. But as a comparison, if the hydrogen atom is produced from the gas phase and the amount of a gas hydrogen usually is limited. So sometimes the adsorption hydrogen to the absorption hydrogen, this process is also reversible. Go inside can also go outside. So, and after hydrogen goes into the steel inside, it's tended to occupy the lattice voids first. And after the voids is become saturated, and then hydrogen is concentrated in the other hydrogen traps, such as a dislocation, green boundary, something like that. So that's why hydrogen from the cathodic source and from the gas source, they have a totally different and hydrogen permeation process. That also tells us a very important conclusion. If you have results you got from the cathodic hydrogen testing, I know there is a lot of the testing in this area, and unfortunately, the results cannot directly apply for the gas phase hydrogen. Okay, so this does not apply directly, and you have to develop a new testing method and a new model, and to derive the hydrogen permeation parameter and the gaseous condition. Okay, and after hydrogen goes into the steel from the gas phase, I need to speed up a little bit. And when we use the existing aged pipeline to carry hydrogen, and you have to realize there are additional materials related challenge. So this additional compare with you build a new pipeline. Okay, so what are the new additional challenge? First one, after pipeline serviced in the field for many years, there must be include loss of the corrosion and mechanical defects. So these defects probably is not so bad in terms of the pipeline integrity. So you as a pipeline can tolerate and this kind of the corrosion or mechanical defects, but the pipeline still can be operating. However, these defects are very effective hydrogen traps. So that means for the aged pipeline, hydrogen can become concentrated at the corrosion side and the mechanical damage side, such as the dents and some other metal loss sites. So these sites can accumulate a high hydrogen to cause the hydrogen embrittlement. Okay, so that's the first extra challenge. The second extra challenge, after pipeline is operated for many years, especially in the geotechnically unstable area, especially for Canadian pipelines, is operated in the mountain area, in the Arctic area, the pipe soil interaction can produce a significant strain on the pipe. So from the previous research, we do find a prestream applied pipe steel will easy to attract more hydrogen in the steel. So that's why, and the prestream can increase the sensitivity of the aged pipeline to hydrogen embrittlement. So that's a second additional challenge. Number three, and pressure fluctuation always happen in gas pipelines. So for the natural gas pipeline, we do research stress corrosion cracking and in terms of the pressure fluctuation. But if the hydrogen is introduced, how the hydrogen and the fatigue cracking will interact together to speed up the crack and growth. So you can see, I just quickly going to here, from these two figure on the right side. So if the pressure fluctuation to change the local strain, and you can see hydrogen permeation will be going up. At the same time, if hydrogen is available, and when hydrogen and fatigue cracking interact together, so you can also see the crack growth rate will also significantly going up. So that gives us a very critical question. If hydrogen interact with the fatigue cracking, how can you quantify the interaction in terms of the crack propagation? So I will tell you, this is a major knowledge gap exists in this topic because we do not have much research in this area. Okay, so that's number three. Number four, for the aged pipeline used for the hydrogen transport, how the impurity gas will influence the hydrogen embrittlement, particularly method CH4, okay, CH4. So, and all our research just prove if CH4 is available, it will have a competition with the hydrogen in terms of the absorption on the steel surface, but the energy barrier, energy bonding energy of the methane compared with the hydrogen absorption energy will be different. But the energy difference will depend on the temperature and the percentage of the hydrogen and the methane, and finally will influence how much hydrogen will compete with the methane touched on the steel surface and go into the steel. So this will have a modeling to quantify the competition effect of the methane with the hydrogen permeation. So that's the first impurity gas. Second one, if a little bit of oxygen is available in the gas, so you can see from the literature, the oxygen will be better to block the hydrogen permeation because it will have a surface blocking effect. So this is available in literature. But if the pipeline fluid also include other gases such as CO, SO2, how is the influence? So this is also a knowledge gap. Finally, the water vapor. So this one is very interesting because sometimes the water vapor can increase, sometimes can inhibit the steel embrittlement by hydrogen because the water vapor and can cause corrosion if it's condensate on the steel surface. So this is also a major knowledge gap. Okay, so to conclude my today's talk, I want to use the two important lists and to talk about. To summarize my talk today, if we want to convert existing pipeline for hydrogen service, in order to meet industry needs, we need to develop a technical assessment program. So this program has lots of things we need to include. And I just quickly go through the assessment list. We need to evaluate possibility of molecule hydrogen to generate the hydrogen atom and the pipeline condition. We need to quantitatively determine how much hydrogen and will be generated and cover the steel surface. We need to quantitatively determine how much hydrogen from the outside steel go into the inside steel. What is the diffusion and the trapping behavior of hydrogen in the aged pipe steel? And this in terms of the steel metallurgy features. At the same time, the aged steel also has the corrosion and other defects can serve as hydrogen trapping. And next, what is the threshold value of hydrogen concentration to cause a crack as the methodological traps and the corrosion and the mechanical traps? So this is a particular apply for aged pipelines. Next one, I just mentioned, what is the interaction between hydrogen and the fatigue? And how can we assess the influence of the prestream because of pipe soil interaction in terms of the HIC? And of course, it's very, very important. This problem as a hydrogen welding area. Finally, based on all of them, the assessment program supposed to tell the industry what is the optimal operating condition to transport hydrogen and avoid the HE problem. So that's from the industrial leads perspective. Because we have so many gaps, and I also listed the lots of things in terms to fill the knowledge gap. For example, what's the thermodynamic model to calculate the free energy change and the hydrogen molecule dissociation? So this one we have developed. So what's the mechanism for the competition in terms of methane and other impurity gas? So this one is partially developed, but not yet finished. And what is the standard well-accepted method for hydrogen charging in the gas phase environment? This one is to be developed. This one is a very important gap to be filled. Next, the methodological microstructure for the aged pipeline. So that's a lot of the literature give you the information for the steel metallurgy of the old pipe steel. Influence of corrosion mechanical defects on hydrogen trapping. This one is a gap to be filled. So the synergistic effect of steel metallurgy, local stress, and hydrogen on crack initiation. There is a lot of experience in this area, but this knowledge need to consider the real practical condition that gives a new recommendation. So next one, hydrogen atom in fatigue crack. This is a knowledge gap to be filled. Influence of prestream on hydrogen permeation, trapping, cracking. This is developed, and we have researched this topic. And fundamental of welding metallurgy and HIC. There is also extensive literature and research in this area. Okay, the last but not the least, and 1 minute. Selection of pipe steel based on the mechanical strengths, and unfortunately, will never successful to avoid hydrogen embrittlement. Because from today's talk, you will see hydrogen embrittlement actually depends on 3 conditions. Okay, mechanical property is just one of them. All right, so and I know some of the standards and just give the recommendation. If you carry hydrogen, you select which grade of the pipe steel. Unfortunately, I will not agree. Okay, so that's a last but not least. That's the first thing. Second, hydrogen embrittlement will happen under the 3 conditions. So this one will support this understatement. Different from the new or intact pipe steel, the existing pipeline have so many defective features that can make the pipelines more susceptible to hydrogen embrittlement problem. So this must be evaluated. Finally, assessment program must be developed based on the different aspects included in today's talk. Then we can have the overall and comfortable conclusion in terms of the suitability of the existing pipeline for hydrogen service. So that's the end of my talk. And again, I thank this category to organize this event. I'm also very happy to communicate my research and my knowledge with all of you, and also like to have the further discussion. Thank you very much.
Awesome. Well, thanks, Frank. That was a fantastic presentation there. Yeah, a huge amount of knowledge. It's crazy to hear what's been kind of already done, all the work that's done, and still all the work that needs to go with that. So I personally found that incredibly insightful. Lots of really good details on it. So we don't have a huge amount of time for Q&A on this front. You went a little over, but you know what? I think that was worth it on here. So we're going to try and get to as few questions as they have, probably just go a little bit over one on here, but maybe a first question on here. So do you know, how are regulatory bodies looking at this? Have they started releasing any levels of guidance of how operators might want to make the change using old pipelines and for hydrogen service?
Okay, so this is a very good question, and particularly from the industrial perspective. And right now, I just want to say, not mature standards and regulation are developed right now, even in the European countries, because Europe and actually has a big initiative. So even in European countries, there is no mature standards and regulation we can follow. And if we really want to make the conversion, and some companies want to initiate, and I think, and firstly, the specific company will develop a team and assessment program, and to have the trial and a certain conversion project. And after some experience developed, and I will say the regulatory the agency and the bodies and managing the pipeline safety will take over or just got involved in the regulation and the management. And for example, in Canada, and we do have the NEB and CER right now to manage the long distance transmission, and the AER managing the upstream pipelines. So, and based on the specific company experience and these bodies, and will got involved in the next stage.
Okay, so do you know if anybody's actually ever successfully been able to convert an old pipeline for hydrogen service?
As far as I know, in Canada, and we are very careful, and I don't know, I don't have experience in terms of Canadian pipelines. In US, and there are in the Texas and the Gulf area, there is hydrogen natural gas blending pipelines, and they are really used. But this pipeline, this hydrogen actually is mainly used for the refinery. And in European countries, and this is a major area, and the blending hydrogen natural gas pipelines, and in trail and relatively large scale. I will go to Belgium next month, and I will have give a invited talk and to community with the European colleagues and listen to their experience. So I know they have the experience, and but I will very happy to share after back from the Belgium.
No, fair enough. That's good to know on that. So I'm curious, is it possible that you might be able to use something like an internal liner to be able to prevent interaction between, you know, the hydrogen atoms against the steel on it? Can that be applied at all within pipelines to help with that?
That's a very good question. And actually, I was also approached by a couple of companies and to talk the same thing, to apply the internal liner and for the problem. My answer is always, it's helpful, okay? So if you have the internal liner, it's very helpful, but cannot 100% solve the problem. The reason is internal liner, I will assume, is usually made of the polymer material or composite material. And this material can decrease or slow down the formation of a hydrogen molecule. And please, for the niner material, this is a hydrogen molecule go into this niner. So it can slow down and reduce formation, but cannot 100% to remove this problem. So that's why my answer is very helpful. But in terms of the long-term service of pipelines, and it cannot guarantee the problem can be solved. So that's the first thing. Second thing, of course, and everybody in industry knows, to apply the internal niner will involve lots of the technical challenge and economical challenge.
Oh, absolutely. No, fair enough. I appreciate that insight on there. So going to kind of, you'd mentioned a little bit about the different issues around the welds on that. Do you know, obviously within the industry, we've got lots of different ways with old pipelines of how they were manufactured between low frequency ERW, high frequency ERW, and DSAW welds. Do you have any comments of some of the threats that might happen using those different kinds of pipelines with hydrogen?
Okay, so when you talk about this one, I just quickly look at this one. So can you please, Brad, briefly repeat this question, please?
Oh, absolutely. No. Okay, so thinking about repurposing old pipelines, and we have lots of different kinds of ways they've been manufactured, especially the main blend with the long seam on it. You know, we've got ERW, DSAW, spiral end pipe. Any thoughts on potentially if there's some that are suitable for hydrogen services, some are not, or if there are huge gaps within that area of studying?
Yes, I think so. And because, as I mentioned in my talk, there is a big knowledge gap and a lot much results are available and currently to help us to have the evaluation. So I will think and complete the evaluation, and in terms of all the potential options will be conducted, and to have the results and the data available and to give the industry recommendation. Yes, I believe so. So, and lots of things to be done, but right now we don't have the detailed specific data and to say which one is better than that one. So basically, it's lots of work in this area. Yeah.
Another one of those huge gaps that you're gonna have to help lead to overcome, hey? Moving on here, do you know if there's any tests to help determine, you know, the susceptibility of pipelines for for having the, I guess, hydrogen service, like, sorry, to see how susceptible they might be for the hydrogen to evolve into the steel and all that kind of stuff, and to be able to create hydrogen-induced cracking?
Yes, there's actually, if you research the literature and the industrial reports, actually hydrogen-induced cracking or hydrogen embrittlement actually is an old topic. But I will say almost all the available results, not all, I will say over 99% of the available results is come from the, I call the cathodic hydrogen. That's produced from the, for example, corrosion reaction or overall cathodic overprotection, or some other sources. So, and when hydrogen is produced by this source and introduced in the steel, we do have the mature technology to evaluate the susceptibility of hydrogen-induced cracking and hydrogen embrittlement. So, for example, we can evaluate the fracture surface and perform the tensile test and also the different other mechanical tests. But the challenge for hydrogen pipelines is environment is a gas, a high pressure hydrogen gas, not the liquid phase. So right now, my comment is in terms of the gas environment, if we want to perform the hydrogen permeation test to get the relevant parameter related to the hydrogen from the gas phase going to the steel, we do not have a standard method available right now. I do have some of the literature and perform the hydrogen permeation test from the gas phase, but this method, and they are not universal. Sometimes the results even and controversial each other. So that's why it's very critical to develop a standard method and evaluation model, and in terms of hydrogen generation and hydrogen permeation from the gas environment.
No, that's fair. No, that's yeah, that's a good tricky situation. So with that, we've got we're a little over time here, so I'm just going to wrap it up here with one last question. We've got a huge audience here today. I think it's another new record on here, so I appreciate everybody joining in. A massive amount of questions. The questions are coming in faster than we can knock them out, so I appreciate everybody's involvement on here. But maybe with the with us running out of time here, I'll ask one last thing. But before that, I noticed that within the chat there, Howard Wallace had made a point that apparently there has been some hydrogen pipelines approved here in Alberta. So he would probably know a little bit about that. Anyways, I know maybe one last question on here. So on your slide 22 there, you were kind of showing the different conditions of how hydrogen can be absorbed in the steel. Do you have any basically kind of essentially rules of thumb of what would be the optimum parameters for operating between your temperature and your pressure and your hydrogen concentration and that kind of stuff on there that people might want to look for?
That's a very important and a practical question. And yes, and for the safety of the pipeline to carry hydrogen with the natural gas, and basically I just summarize the 3 conditions for hydrogen embrittlement and hydrogen concentration. So this one depends on the operation condition, such as the partial pressure of hydrogen in the fluid, right? So you can adjust the percentage of hydrogen to methane and to change the potential amount of hydrogen goes into the steel. But this one is just one of them. Another one, we also need to think about the stress condition of the steel. For example, what is the operation pressure? And what is the surface condition of the steel? So if there is a mechanical damage, and there will be a stress concentration in this area. So we need to model and calculate the local stress concentration. So that's number 2. So hydrogen and stress, and number 3, that's a steel metallurgy. And lots of the current standards recommend the low-grade steel in the hydrogen service. So this one, just one of the conditions. Generally, low-grade steel associated with a good conductivity. And elongation and ductivity. So this is better in terms of the prevention of the hydrogen-induced cracking problem. So my answer, based on this one, the 3 conditions, that means you have to have the comprehensive evaluation in terms of steel grade, operating condition, and then you can give the recommendation. What is the best operation conditions, and make the hydrogen embrittlement problem not happen under the given condition. So that's why assessment supposed to be comprehensive, not based on the single parameter or single criteria.
Oh, okay. No, that's a very practical solution. Like you said in your last couple of slides there, just the level of analysis that needs to go in if this was ever to be achieved on it with an existing pipeline. So it's a lot to consider. This is a huge amount of information in a very short period of time. And yeah, obviously it's something that a lot of both pipeline engineers and pipeline integrity engineers are going to have to be very cognitive of over the next several decades as we start to see more hydrogen pipelines come into work. So I mean, your research is and work you're doing on this is super valued and appreciated, and I think I speak for everyone here. And thank you so much for all your time that you dedicated to this, and your presentation was fantastic. So thanks again. So with that, we're going to close up here today on it. Thank you everybody again for joining here today. I apologize that we didn't get to answer probably the majority of the questions on here. A great active group, so much appreciated on that. Maybe with that, I'll close up and just mention here today that, you know, we've definitely got, even though people are starting to look to head back into office, into our offices and such, we're still looking on putting on webinars throughout the summer. So keep following us on LinkedIn to see what kind of upcoming presentations. One I can talk about on here is that we're going to have a technical panel of a variety of different experts to talk about non-metallic pipelines, and you can look for that on Friday, March 18th. So book that on your calendar.
Oh, sorry, Brett. Just give me one more minute, please.
Oh, absolutely. Go ahead.
Okay. Okay. So because of the limited time, and I can see there is lots of questions, I don't have time to answer, to have the interact with you. So if you are really interested with this topic, and please contact me by email. Email is the best way to reach me. So that's the first thing. The second thing, and start from today, I will have lots of opportunity to present the hydrogen pipeline topic in Canada. And I can tell you there is a tons of events and activities. And I'm honored to be invited to talk this hydrogen pipeline topic. And for example, in Edmonton, the Least Northern Area West Conference, I will give the keynote on hydrogen pipelines. I will also talk in Montreal chapter and Ontario chapter through the ASM Canadian Council, and all of them is focused on the hydrogen topics, hydrogen pipeline topics. And if you are interested, and you can also join these events, and hopefully have more time to have an interaction. Yeah, thank you, Brad.
Oh, that's awesome. Thanks for that addition on there. I guess lots of good chances to be able to find out more on that. So yeah, so to everybody asking, of course, this video will be there posted up on YouTube within a couple of weeks. And so have you a good reference on it. And then be sure to check out some of Frank's other talks that he has coming up on here, such as in the Edmonton, is what I mentioned. So thanks again, everybody. Really appreciate everybody coming out. Have a wonderful weekend, and we'll talk to you next time.
Thank you. Bye.